Here we go. Okay, so again, let me reiterate that for Courtney here. So we heat up the can. Steam starts to expand, bouncing around all over the place. So same thing with the balloon. The pressure increases, volume increases. Everybody's good with that, right? You can kind of visualize it and make some sense, I hope. Okay, then what do we do? So the second step here is we place a flask and the can in ice water. And what does that do? That drops temperature dramatically, right? So temperature drops, temperature in the balloon and can drop quickly. What do gases do when you cool them down? They can liquefy, but before that, I keep using the same analogy. When you heat up a gas, it expands. They get away from each other. They're hot. They don't want to be near each other. If you cool a gas down, what do? They condense like what? Penguins. I really want you to think that. Okay? Penguins huddle together for warmth when it's cold. All right? Goats do it. Sheep do it. I suppose if you guys were all trapped in the wild and it was cold, I would think you would huddle together as well. Maybe not. Maybe you don't like each other. Maybe that's weird. But you would if you had to survive. The point is, atoms do the same thing. Gases do the same thing. They huddle together. So, place flask and can in ice water. Temperature in balloon and can drop quickly. The gas particles condense. All right, who wants to explain what happened? I can lead the horse to water, but I can't make it drink. I'm not calling you guys horses, but that's the analogy. I'm bringing you right to it. Now you guys gotta take it the next step. So I'm gonna explain. Particles condense, the gas particles condense in the flask and in the balloon and in the can, so particles are now coming together. Why did the balloon go into the flask? Why did the can get crushed? Your turn. And by the way, this is explaining all the gas laws at once, which we're going to learn, and it also helps understand the homework. So, sometimes I wish I had a soundboard, and I would hit the Jeopardy button right now. That's what's happening.
The little tune thing? I wish I could.
So you guys should be thinking. Yes?
I just said that it was because the gas particles condensed.
Yeah, but I need, all right, so we know it condensed, but why does that mean? First of all, who thinks the balloon was sucked into the flask? Some people, not sure. Who thinks the balloon was pushed into the flask? I mean, I didn't push it in. I was holding it so it had a better angle. So like the balloon was kind of flopping around. I was just holding it so it would go in easier. All right, but I didn't actually, you didn't see me stuff it in there, did you? No, I didn't do that. Okay. Pushed in. Was there some imaginary person pushing the balloon in? We can't see it? Did you say the hand of God? It's actually my superpower. I can mentally make things happen. High to low what? Yes, it does. It has everything to do with that. So Nicole, finish that thought. Very good. Right. So when we had that flask and we put the flask in the cold water and the balloon started collapsing, the pressure inside that flask, so now we have the can. I can't really draw a flask very well, but okay. There's our balloon, okay? So we put it in that. So here's the ice water, okay? Ice water. All the gas inside here and in here are condensing. So the air pressure is actually 1 atm. The pressure inside the balloon and inside the flask drop below 1 atm. So inside the flask, maybe it's 0.5 atm. So the pressure inside the flask is less than the air pressure. Air pressure, gases in general, always move from high pressure to low pressure. So if you go up to a balloon and you pop it, the air always comes out. It doesn't go into the balloon. Imagine that. You pop a balloon and air goes in. All right, that would be weird, right? It's the opposite, high pressure to low. The same concept here, except it's opposite of what you would think. The pressure in here drops because you're cooling it down. So the air pressure, I know this is hard to understand, but you saw it with your own eyes. The air pressure pushes the balloon into the flask because it's high pressure out here in the room, low pressure in here. So the balloon, a lot of kids think it gets sucked in. It got pushed in by the air outside. So that's why it's a cool demo, because you just don't expect it. That's the same reason the can crushes. The air pressure is greater outside. When you put this in ice water, right, we flip it upside down. In here, this one worked even better. This one was kind of slow motion. This one, all the gas in here condenses so fast that the pressure is almost a vacuum. It's almost zero. There's almost no pressure. So all the air pressure out here is pushing on the can from all directions, and it just crushes it because the pressure in the room is greater than the pressure in the can. So lots of chemistry involved here. You heat it up, it expands, pressure goes up. Cool it down, they condense, pressure drops to almost zero. So now the air pressure is greater, so it crushes the can, and it won't crush the glass because it's too rigid, right? But it pushes the balloon. That's the weak spot, the balloon, so it pushes the balloon in. So to finish what we were writing, the gas condenses. So then here's our explanation. The air pressure in the room is greater than the air pressure in the can and the balloon. So the balloon is pushed into the flask and the can is crushed. Oops. The can is crushed. It's a cool demonstration. I have a video on my website. If I have time, I can show you, but we got to go through the homework quick. It took a long time explaining all that, but it's worth it. Because if you understand those two demos, you understand how temperature can affect pressure and volume, and how pressure differences can cause gas and air to move, which is obvious of the can being crushed. The pressure is causing that. That really explains a lot of things we're going to be doing. So it was worth the time, I hope. But I have a video of a giant tanker on a train. Huge. You know, you see them on trains all the time. They're like cylinder shaped, and they're usually with gases or liquids inside them. And this one is just sitting on the tracks or wherever it is, and the whole thing crushes. Because this happened to it. It's pretty cool. I mean, it's monstrous. It makes a huge noise. The whole thing shakes. It's kind of cool. That's just kind of proof of how strong pressure can be. All right, so hopefully that makes sense. Questions on that? Okay, homework. Go to the homework now. I'm going to zip through this so we can take some new notes. Got to make sure you have homework, you know? Got to make sure. Can't let you go home and
Have fun.
have fun. Just, you know, read the chemistry book at your leisure. Leisure is the word, Mike. Leisure. All right, 14. Relationship among pressure, temperature, and volume of a fixed amount of gas. What they're getting at is if you increase temperature area, what happens to pressure? Gets greater, right. So we're going to kind of do two things at once just because you can handle it. You got your notes out, I hope?
Yeah.
We're going to draw 3 graphs in our notes right now. 3 graphs. 1, 2, and 3. Now, this graph, we're going to put temperature and pressure on the X and Y. This graph, temperature and volume. And then this graph, we're going to put volume and pressure. So PTV, pressure, temperature, volume. Now this one, pressure, temperature, volume, this is going to be at constant volume. So if we hold the volume constant, so let's say we have a container, it's right here. If I put the top on this thing, nothing's getting in, nothing's getting out. This is constant. It's about 32 ounce, so it's, what is it, like 1,000 milliliters, about, okay? About a liter? Yeah, about a liter. So there's about a liter in here, I believe. So that's constant. If that was filled with just air, I took all the water out, and I heated it up, what happens to the air in that? Would the pressure go up? Yes. Ariel just told us. So what would that graph look like? If temperature goes up and pressure goes up, that's the relationship. What would it look like? Hannah motion like that. Directly related. It's a direct relationship. Now temperature and volume at constant pressure. So in this room, this is like the balloon on top of the flask. The balloon on top of the flask. The pressure in the room is constant, 1 atm, it's not changing. We heated up that vapor, we heated up the gas. Did the balloon start taking up more space? Yes, the volume went up. So Watson, what does that graph look like? Yes, you're right, say it. Does it look like this? Yes. I thought that's what you were going to say, so that's why I said say it. Yes, temperature goes up, volume goes up. Also directly proportional. We'll do this one in a minute. Okay, so temperature goes up, volume goes up. Temperature goes up, pressure goes up. 15. Which of the three variables that apply to equal amounts of gases are directly proportional? Right here. Temperature, volume are direct, temperature, pressure. All right, here's a big clue here. Matt Payne. Which relationship is inversely proportional?
Pressure and volume.
Very good. It's the only graph we have left. So this is at constant temperature. Constant temp. And you saw this, again, the demo. I keep going on and on. I hope you're not getting sick of me talking about it. But it really explains this stuff. It's hard to see the air. You can't see it. It's hard to understand pressure because you can't see it. You can't even really feel it. Okay? So, except when you breathe. You breathe in, you can feel the pressure a little bit. So, the analogy with the demos, trying to help you see this, I hope it's really helping. So, you saw this. When I cooled the gas down, both of these dropped to almost zero, right? But the air pressure stayed the same. So when I cooled the gas down in that can, the volume shrunk, the pressure dropped, but the pressure out here was the same, so it crushed the can. So when we have a lot of pressure put on that can, what happened to the amount of space the can took up? You're not following me.
Condensed. It went down.
So the can, when it's not crushed, takes up a certain amount of space. If you crush it, it appears to take up a little bit less space because it's smushed into a ball. Would you go with me on that? Okay? So what am I trying to get you to understand? If you squeeze a gas, if you compress a gas, does it take up more or less space? Less. Right now you guys are taking up a certain amount of space in the room. Okay? If we were to push all the desks together and make all of you kind of get in one clump in the middle, you would take up less space in this room right here. Would that be fair to say? Okay. That's why this graph looks like this. If you have a high pressure, lots of pressure, it will crush the gas and it will take up a very little amount of space. Remember, gas particles are very far apart. So if you push them together with lots of pressure, lots of force, they take up less space. That's what I'm explaining with you in the room. Right now, there are spaces between you. We could take care of that. We could compress you, and you would take up less space. So this is the inverse. And if you release the space, okay, go slash someone's tire. Don't do that, Adam. All right, don't do it anymore. So, you slash someone's tire. Air comes out of the tire. What are you releasing on that tire? Pressure. Look up here. Low pressure. High volume. The gas in a tire is very compressed into that area. If you pop it, all the air comes out and tries to fill up the whole world. It tries to fill up the atmosphere. So it starts spreading out immediately. And remember, gases like to expand, ideal gases, right? They like to be ideal. All right, so these are the three gas laws that you need to know. This one's called Boyle's Law. This is called Charles. This is called Lusak's Law. You don't need to memorize the names of the laws, but that's the law. As pressure goes up, volume goes down. As temperature goes up, pressure or volume goes up. As temperature goes up, pressure goes up. So these are the relationships that you need to know. Okay, back to the homework. 17. Why gases such as the oxygen used at hospitals are compressed? Why must compressed gas? Okay, so why do we compress oxygen and keep them in those tanks? So it's pure, good. Here's an easy answer. How else are we going to transport oxygen gas? You're just going to have these giant balloons that you drag around with you, right? Hook up tubes to your nose, and just literally like the hot air balloon following you. You can't go into it, but you can't live like that. That's crazy. So we compress it so it's easy to move around. It's portable. And you can put a ton of gas in those things. My grandmother used to be on oxygen, and or was on oxygen. And one container, you know, we would go to doctor's appointments, we would, you know, whatever, go out for a day, and the whole tank would last most of the day, and then, you know, probably some of the next day. So they last a long time. There's a lot of oxygen. So it's easy to move them around. But now Hannah's going to help us. Actually, you've already helped us. Who's going to help us now? Trevor. Why do we have to, where does it say? Why do we shield it from temperature? Oh, yeah, because it'll catch on fire, right? So if you get oxygen gas near high temp, it could burn because it's flammable. Actually, what else could happen?
Gas might expand and it might blow up.
Yeah, expand and blow up the container. Good. Next question. What must happen to compress oxygen before it can be inhaled? You guys ever seen one of these oxygen tanks? There's a contraption you have to put on top of it. You don't just hook a tube right up to the side of it and then inhale that. If you did, you would die, like pretty quick. Why do you have to do something? That contraption does something to it. It depressurizes it. Think of it this way. Inside the container, so inside the container here, okay, all right, you have the oxygen gas very close together, very compressed, okay? When it comes out, what's the first thing that gas wants to do? What do gases always want to do? Expand. So these particles, instead of being that close, want to be that far apart. If you were to inhale this gas directly from here into your lungs, it's going to go into your lungs for a fraction of a second, being this close together. As soon as it gets in here, what is it trying to do?
Expand.
Expand, and it will blow up your chest. You will literally blow up. That's, you know, pretty messed up thinking about it. You know, kind of joking, but that's awful to think about. Okay, do I actually know if literally your whole inside would blow up? I don't know. But bad things would happen. So you have to let the gas expand a little bit, then breathe it in. Does that make sense?
Yeah.
That's actually, I like that question because that's something, a lot of times we talk about things in here that in my brain, I can think of a million examples in real life that this stuff applies to, but you can't always do that, so that's my job, right? Try and relate it. So I think this is a good one because a lot of people are on oxygen. You know, at some point, maybe you will be when you're 90 years old. I don't know, who knows? But the concept there is important to understand. All right, 51, 52 here real quick. Hopefully I can get this done. 51. All right, if two variables are inverse, what happens to the value of one as the value of the other increases? So this graph right here. If one goes up, Mike Flower, what happens to the other one?
Power.
Yeah, if one variable, if one of these goes up, what happens to the other one?
What's that?
Goes down. Good. 52. If two variables are directly proportional, if one goes up, Mike, what happens to the other one? If we're directly proportional, one goes up, what happens to the other? Up. They both go up. Good. 54. Units for P, V, and T. P, you should have ATM or KPA. ATM or KPA, kilopascal or atmosphere. Volume, liters or milliliters. And temperature, Kelvin. Celsius doesn't belong here. Kelvin is what we're dealing with gases. Kelvin. All right, real quick. The bell's going to ring. And I got to give you this worksheet. Due tomorrow. Number 1, the answer was D. We'll pick up with that tomorrow. All right, well, we didn't get as far as I wanted, but that's okay. I think it was good stuff we were talking about there. So this worksheet's due tomorrow. Just the circled problems. Just the circled ones. There's not many. Yeah, I got it. Just the circled problems. There's like maybe 7 or 8 of them. Okay, so that's due tomorrow. Have a wonderful day.